In 1897, one small boat made the Royal Navy look like fools in front of the entire world. And the man who did it wasn't even a sailor. The date was the 26th of June. The place was Spithead, off the coast of Portsmouth. Queen Victoria's Diamond Jubilee Naval Review, the grandest display of sea power in human history. 165 warships stretched across 25 miles of gray water. Battleships with 12-inch guns, cruisers bristling with artillery, destroyers fresh from the shipyards. The pride of an empire that ruled a quarter of the globe. Foreign ambassadors filled the observation decks. The Prince of Wales stood in for the aging Queen. Every admiral, every diplomat, every correspondent who mattered was there to witness Britain's dominance. The fleet sat in perfect formation, steam rising from hundreds of funnels, brass gleaming in the summer light. This was choreographed supremacy, order, discipline, power. Then, from somewhere beyond the gray horizon, came a streak of white foam. A narrow, black-hulled vessel, no bigger than a rich man's yacht, tore through the lines at a speed that made officers freeze mid-sentence. The boat carved through the formation like it was mocking them, wake spreading white across the gray water. Someone shouted orders. A patrol craft gave chase. It wasn't even close. The intruder just accelerated, zigzagging between battleships, close enough to read the hull numbers, faster than anything the Navy could build. 34 knots. The fastest ship in the Royal Navy could barely manage 27. This thing was playing with them. 10 minutes of chaos. 10 minutes of the greatest fleet on Earth, looking absolutely helpless. Then the boat vanished into the haze, leaving nothing but questions and a wake that wouldn't stop spreading. The newspapers called it the most audacious stunt in naval history. The Admiralty called it a bloody outrage. But the man at the controls, he called it proof. And what he'd just proven would change warfare forever. His name was Charles Parsons. And this is how one engineer with a temper made Britain unstoppable. Charles Algernon Parsons was a walking contradiction wrapped in oil-stained sleeves, the son of an earl, born into one of the most prestigious scientific families in Britain. And he chose to spend his days on factory floors with grease under his fingernails, building machines that most aristocrats wouldn't understand if you drew them a diagram. His father was the 3rd Earl of Ross, the astronomer who'd built the largest telescope on Earth. His childhood home was Birr Castle in Ireland, filled with gears, lenses, and the smell of hot metal. At 12 years old, most boys from wealthy families were learning Latin and playing cricket. Charles and his brothers built a steam-powered carriage that hit 10 miles per hour and terrified the servants. 4 horsepower, hand-built, a machine that moved under its own power, designed by children who understood engineering better than most adult craftsmen. But here's the thing nobody expected. The boy grew into a man with an explosive Irish temper and the social skills of a recluse. Colleagues later described him as extremely diffident, so shy he could barely handle public speaking, yet put him in a workshop and he transformed. He'd spend 16-hour days measuring blade angles to within a hair's width, testing steam pressures until his hands blistered, rebuilding the same component 7 times because the 6th attempt wasn't perfect enough. This wasn't a gentleman scientist dabbling in experiments. This was obsession. When his car broke down in the Northumberland moors, miles from help, Parsons didn't panic. He dismantled the bent shaft, lit a fire using stones as both forge and anvil, hammered the metal straight with rocks, reassembled the entire mechanism, and drove home. No complaints, no drama, just problem, solution, move forward. That was how his mind worked. Pure intuition backed by relentless hands-on work. After graduating with first-class honors in mathematics from Cambridge, he made a choice that shocked his entire family. He became an apprentice, the son of an earl, taking orders from foremen in a Newcastle engineering works. His aristocratic peers thought he'd lost his mind, but Parsons understood something they didn't. You can't revolutionize an industry from a drawing room. You need to know how metal behaves when it's stressed, how steam moves through pipes, how bearings fail under load. The only way to learn that is by doing it yourself, and Parsons was never afraid to get his hands dirty. By 1884, he'd worked his way up to head of electrical development at Clark, Chapman and Company. Still modest, still awkward in meetings. But in the workshop, he was building something the establishment thought was impossible. And that's when the real fight began. Britain's empire didn't run on pride or tradition. It ran on coal, steam, and the ability to move faster than anyone who wanted to challenge it. By the 1880s, that advantage was slipping. The Royal Navy ruled the world's oceans with over 300 warships, more than the next 3 navies combined. But there was a problem nobody wanted to say out loud. Every single one of those ships was powered by piston engines that were hitting their absolute physical limit. The reciprocating steam engine, the technology that had built the Industrial Revolution, was tapped out. Engineers had squeezed every ounce of efficiency they could from pistons slamming back and forth thousands of times per hour. The machines were enormous, heavy, and they shook ships apart at full speed. Worse, they wasted nearly 70% of their fuel as heat and noise. Germany wasn't sitting still. Neither was America. Both nations were building fleets, studying British designs, and investing heavily in new propulsion technology. The Kaiser's naval architects knew exactly what the Royal Navy knew. Whoever cracked the next generation of marine power would dominate global trade routes, project military force faster, and control the future. The technological gap that had kept Britain untouchable for decades was closing fast. This wasn't just about engineering pride, it was about survival. Britain imported food from India, Australia, Canada. Raw materials from Africa. Manufactured goods flowed through shipping lanes that had to stay open no matter what. Lose naval supremacy, and the entire imperial system collapsed. Every port, every colony, every trade agreement depended on the Royal Navy's ability to arrive before anyone else and hit harder when they got there. And the piston engine couldn't deliver that anymore. Ships were getting bigger, but not faster. Armor was getting heavier, but propulsion wasn't keeping up. The Navy needed a breakthrough, something that could turn fuel into motion without tearing itself to pieces in the process. They needed more speed, more range, and less weight. They needed it yesterday. Parsons saw the problem clearly. Every piston stroke wasted energy. Steam expanded once, pushed a rod, and most of its pressure vanished into the exhaust. It was violent, inefficient, and fundamentally limited. What if, instead of forcing steam to stop and start, you let it flow continuously? What if you could harness that pressure across multiple stages, extracting energy smoothly instead of in brutal, wasteful bursts? The idea wasn't new. Engineers had theorized about rotary steam engines for decades, but nobody had made one work at scale. The forces involved were immense. The precision required was beyond what most workshops could achieve. The establishment dismissed it as theoretical fantasy, too delicate for the real world of saltwater and combat stress. Parsons didn't care what they thought. He had a solution. He just needed to prove it worked. But first, he had to build it. And the people with the money to fund him thought he was chasing a dream that would bankrupt anyone foolish enough to believe in it. The Admiralty's response was brutal and immediate, impractical, too delicate for naval service, unproven. The committees didn't even bother with polite refusals. They simply dismissed the turbine concept as engineering fantasy, the kind of thing clever men sketched on paper but couldn't build in the real world. One senior officer reportedly called it a toy for inventors who'd never seen a warship under fire. Another said rotating blades would shatter the first time they hit rough seas. The message was clear. Don't waste our time. Parsons had walked into those meetings with calculations, steam tables, and prototypes. He'd explained how continuous expansion could extract far more energy than piston strokes ever could. He'd shown them the mathematics. They nodded politely and showed him the door. The Royal Navy had been building piston engines for half a century. They had shipyards, supply chains, and thousands of engineers trained in reciprocating technology. Why would they gamble on an unproven system from a man who'd never designed a warship? The rejections kept coming. Private investors didn't want to touch it. Shipbuilders said the precision required was impossible to manufacture at scale. Even colleagues at Clark, Chapman warned him to focus on proven technology. The turbine was too risky, too expensive, too radical. If it failed publicly, it would destroy his reputation and bankrupt anyone involved. But Parsons had a temper, and being told something was impossible only made him more determined. If the establishment wouldn't fund him, fine. He'd fund himself. In 1889, he left Clark, Chapman, and founded his own company, C.A. Parsons and Company in Newcastle. The price of independence was steep. He lost access to his original patents, had to start from scratch. But now, nobody could tell him to stop. The technical problem was vicious. His first turbine, built in 1884, was barely functional. 1.6% efficiency, 7.5 kilowatts of output. Pathetic by any measure. The rotating blades couldn't handle high-pressure steam without distorting. The shaft bearings wore out in hours. Steam leaked from every joint. It worked in theory, but the real world kept finding new ways to break it. Most engineers would have quit. Parsons rebuilt it, then rebuilt it again. And again. He measured everything obsessively. Steam temperatures to the degree, blade angles to fractions of a millimeter, bearing clearances so tight they had to be assembled in temperature-controlled rooms. He trained his own machinists because nobody else could work to the tolerances he demanded. His workshop became a laboratory, where failure wasn't shameful, it was data. Slowly, brutally, the efficiency climbed. 3%, 5%, 8%. By the mid-90s, his land-based turbines were generating electricity more cheaply than any piston engine on the market. Power stations started buying them. The technology worked, but convincing the Navy was a different battle entirely. They still wouldn't listen. Parsons needed a demonstration so dramatic, so undeniable, that even the most stubborn admiral couldn't ignore it. He needed to build a ship, not a model, not a test rig, a real vessel that could prove the turbine's superiority in conditions the Navy couldn't dismiss. So he gambled his entire fortune on a boat nobody asked for. But first, he needed money, and the only way to get it was to prove the turbine could make a profit on land before risking everything at sea. In 1890, Parsons opened the Forthbanks Power Station in Newcastle, the first facility in the world to generate electricity using turbo generators. It was a calculated gamble. If the turbines failed publicly, the entire concept would be buried. If they worked, he'd have proof the establishment couldn't ignore. The machines hummed to life, rotors spinning at 18,000 revolutions per minute, and the lights came on across the city. No explosions, no breakdowns, just smooth, continuous power that cost half what piston engines charged. The numbers told the story. Within 2 years, his turbines were hitting 12% efficiency, double what his first prototype managed. By 1894, 15%. By 1897, 20%. Every percentage point meant cheaper electricity, lower fuel costs, and higher profits for anyone willing to buy his machines. Power companies started placing orders. Factories followed. The technology that admirals had dismissed as impractical was now lighting homes and driving industrial equipment across Britain. Parsons didn't celebrate, he measured. When a colleague asked him years later what made his turbines succeed where others failed, his answer was brutal in its simplicity. We measured what others assumed. While competitors relied on theory and guesswork, Parsons built instruments to quantify everything. He invented the torsion meter to measure the exact force his turbines produced. He mapped steam flow through blade passages. He tested bearing materials until he found alloys that could survive constant rotation at speeds that would destroy conventional metals. His workshop floor became a kind of laboratory cathedral. Machinists worked to tolerances measured in thousandths of an inch. Blade angles were calculated to fractions of a degree. Every component was weighed, measured, tested to destruction, then redesigned. Parsons would spend entire days watching a single bearing run, timing how long it took to fail, then rebuild it with microscopic adjustments. Failure wasn't shameful, it was information. And Parsons was collecting data faster than anyone in the industry. But success brought new problems. Other engineers saw the profits and started copying his designs. Patent battles erupted. Competitors claimed they'd invented similar systems first. Legal fights drained time and money. Parsons fought back with the same obsessive precision he used in engineering. He documented every iteration, every test, every incremental improvement. When challenged in court, he buried opponents in technical evidence they couldn't dispute. He won his patents back and even earned something almost unheard of, a 5-year extension granted by the government in recognition of national importance. By 1893, C.A. Parsons and Company was profitable, respected, and generating megawatts of power across Britain. The turbine had conquered electricity generation. Parsons had proved the skeptics wrong and built a fortune doing it. Most men would have stopped there, declared victory, enjoyed the wealth. Parsons stared at the ocean and saw a bigger challenge. Marine propulsion was a different beast entirely. Ships faced salt water, violent seas, combat stress, and speeds that would expose every flaw his land turbines could hide. The forces were immense. The stakes were even higher. One public failure at sea would destroy everything he'd built. But if it worked, if he could make a turbine-powered ship outrun the entire Royal Navy, the establishment would have no choice but to listen. In 1894, construction began on a vessel that would either prove him a genius or bankrupt him trying. Her name was Turbinia, 103 feet long, 9 feet wide, displacing just 44 tons. A slender steel hull built by Brown and Hood at Wallsend, designed by a man who'd never built a ship before in his life. Parsons had sketched the design himself, calculating hull resistance and power requirements using models he tested in water tanks. Everything looked perfect on paper. 3 turbines connected to a single shaft. driving one massive propeller at 2,000 revolutions per minute. The mathematics promised speeds the Navy couldn't match. The first sea trials were an absolute disaster. April 1894. Turbinia slid into the Tyne with Parsons at the controls, steam pressure building, expectations sky high. The turbines spun up beautifully, smooth and powerful, exactly as designed. The boat moved forward, and then just kept moving forward at a pathetic, humiliating crawl. Top speed barely touched 20 knots, slower than some of the Navy's oldest destroyers. Parsons opened the throttles wider. The turbines screamed. The shaft vibrated so hard it threatened to tear itself apart. The boat didn't go any faster. Something was catastrophically wrong, but nobody knew what. The turbine was producing power. The instruments confirmed it. The shaft was spinning at the correct speed. Yet, somehow, all that energy was vanishing before it reached the water. Parsons docked the boat and started tearing it apart, looking for mechanical failures. Nothing. The bearings were fine. The shaft alignment was perfect. The propeller blades showed no visible damage. Every component was working exactly as designed, and the boat was still useless. For months, Parsons ran test after test, changing propeller designs, adjusting blade angles, trying different materials. Nothing worked. 20 knots. Always 20 knots. The boat hit an invisible wall and refused to go faster no matter what he did. His fortune was draining into a vessel that couldn't beat a paddle steamer. Investors started asking uncomfortable questions. Colleagues whispered that maybe the Admiralty had been right. Maybe turbines were fine for power stations, but hopeless for marine propulsion. Then Parsons did something nobody had thought to try. He built an instrument to measure the exact torque the turbine was applying to the propeller shaft. If the engine wasn't producing enough power, he'd see it in the numbers. If something was stealing energy between the turbine and the propeller, the data would show where it went. He bolted the device to the shaft, took Turbinia back out, and opened the throttles. The readings made no sense. The turbine was producing full power. The shaft was delivering that power to the propeller. But the thrust pushing the boat forward was a fraction of what it should be. The energy was disappearing at the propeller itself, and Parsons suddenly understood what he was looking at. The propeller wasn't gripping the water. It was spinning so fast it was creating a vacuum behind the blades, a void where water should be. The phenomenon had a name: cavitation, and it was killing his ship. The Royal Navy was dealing with the same problem on their newest torpedo boats, but they didn't understand it either. Parsons attacked it like he attacked everything else. He built Britain's first cavitation tunnel, a sealed chamber where he could observe propellers spinning underwater at high speed, watching how bubbles formed and collapsed. He photographed the phenomenon, measured the pressure differentials, calculated exactly how fast a blade could move through water before cavitation destroyed its efficiency. The solution was counterintuitive. Instead of one large propeller spinning at 2,000 revolutions per minute, he needed multiple smaller propellers, each spinning slower, distributing the load so no single blade created enough vacuum to cavitate. He ripped out the entire propulsion system and rebuilt it from scratch. 3 turbines, 3 separate shafts, 3 propellers per shaft. 9 propellers total, each one carefully designed to operate just below the cavitation threshold. April 1897. 3 years after the first disaster. Turbinia went back into the water with her new configuration. Parsons stood in the engine room, watching steam pressure climb, knowing this was his last chance. If it failed again, the project was finished. He opened the throttles. The turbines spun up. The 9 propellers bit into the water like teeth. And Turbinia exploded forward like she'd been shot from a cannon. 30 knots, 32, 34. The hull lifted slightly as she planed across the surface, spray erupting in white sheets, the world blurring past. She held that speed for a measured mile, then kept going. Parsons throttled back, grinning like a maniac, and checked his instruments. The fastest ship on Earth, and she was barely breaking a sweat. Now, he just needed the Admiralty to see it. And 2 months later, Queen Victoria's Diamond Jubilee gave him the perfect stage. Parsons didn't show up at Spithead by accident. 3 weeks before the review, he'd received a quiet visit from a mid-ranking naval officer who spoke very carefully and left no paper trail. Certain people within the Admiralty were tired of watching committees strangle innovation. They couldn't officially invite Turbinia. That would be career suicide. But if a private vessel happened to demonstrate unprecedented speed during the review, and if foreign observers happened to witness British engineering superiority, well, nobody could be blamed for an unauthorized intrusion they'd tried to stop. The officer smiled, shook Parsons' hand, and walked out. The message was clear. Do it, and make it spectacular. The morning of the 26th, Parsons loaded George Baden-Powell onto Turbinia along with a skeleton crew. Baden-Powell was perfect for the job, well-connected, credible, and someone whose word the press would trust. He'd serve as witness to whatever was about to happen. The boat sat just beyond the formation, engines cold, waiting for the right moment. Parsons watched the Prince of Wales begin his inspection, the ceremonial speeches droning on, and then he gave the order. Fire the boilers. Steam pressure climbed. The turbines started spinning, that distinctive smooth hum that sounded nothing like a piston engine's rhythmic hammering. Baden-Powell gripped the rail as Parsons opened the throttles and Turbinia lunged forward. The acceleration was vicious. Within seconds, they were doing 20 knots. Then 25, 30. The bow lifted slightly and spray exploded outward in white sheets. Baden-Powell later wrote that the most remarkable thing wasn't the speed, it was the complete absence of vibration, like riding a wave instead of a machine. They hit the formation doing 34 knots, weaving between warships with Parsons at the controls, his Irish temper fully unleashed in mechanical form. He wasn't just demonstrating a boat. He was humiliating every admiral who'd told him to wait, every committee that had dismissed his work, every bureaucrat who'd chosen politics over progress. The turbines screamed. The wake spread like a white scar across gray water. Officers on the battleships shouted orders that meant absolutely nothing. A picket boat roared after them, throttles wide open, engine howling. Turbinia simply accelerated. The patrol craft gave everything it had and got left behind like it was anchored. Worse, Turbinia's wake hit the smaller boat so hard it nearly capsized, crews scrambling to keep from being swamped as white water crashed over the gunwales. The Navy's fastest pursuit vessel drowning in the wake of a yacht. On the deck of the German warship, Prince Henry of Prussia stood frozen, binoculars locked on Turbinia. He wasn't watching entertainment, he was watching the future of naval warfare tear through Britain's fleet. And he understood immediately what Berlin needed to know. This wasn't about speed records, this was about power projection, about who could move forces faster, hit harder, and control sea lanes before the enemy even knew a war had started. The prince turned to his aide and said something that would be repeated in the Kaiser's war rooms within a week. Germany needed that technology, and they needed it before Britain put it in every warship they built. The Times ran the story on the front page the next morning. Extraordinary feat of marine engineering stuns naval review. Other papers called it the most audacious demonstration in British history. One correspondent wrote that watching Turbinia was like seeing a cheetah run through a herd of elephants. Fast, graceful, and utterly untouchable. Within 48 hours, every naval attaché in Europe had sent reports home. The era of the piston engine was over, and one furious engineer had just announced it to the world in the most public way possible. The Admiralty was livid. Publicly, they condemned the unauthorized intrusion. Privately, 3 senior officers visited Parsons' workshop within 10 days. They didn't apologize. They didn't admit they'd been wrong. They just asked, very politely, if he could build something bigger. 8 weeks later, Parsons' workshop in Newcastle was full of men in naval uniforms pretending they'd always believed in turbines. The same Admiralty that had called his work impractical now wanted detailed specifications, performance data, and delivery timelines. Parsons showed them everything. Blade geometry that took years to perfect. Steam flow calculations. The 9-propeller solution to cavitation. He didn't gloat, didn't lecture, just handed them the future and let the numbers speak. In 1899, HMS Viper and HMS Cobra slid down the slipways, the Royal Navy's first turbine-powered destroyers. Both ships were built with Parsons turbines driving them, and both absolutely shattered every speed record the Navy had. Viper hit 37 knots on trials, faster than anything afloat. Cobra wasn't far behind. For the first time, the Royal Navy had warships that could outrun any threat and catch any target. Admirals who'd spent careers dismissing the turbine suddenly found religion. Orders were placed for more turbine vessels. The future looked unstoppable. Then reality hit back hard. August 1901. Viper ran aground off Alderney in thick fog and broke her back on the rocks. 3 months later, Cobra sailed into a North Sea storm. Her hull fractured under stress, and she went down with most of her crew. 2 revolutionary destroyers, both lost within months. Neither tragedy had anything to do with their engines. Structural failures, bad weather, the brutal mathematics of ships pushing speeds their hulls weren't designed to handle. But the old guard saw an opportunity. Committees reconvened. Engineers testified that turbines put too much stress on ship structures, that the technology was too radical for combat conditions, that maybe, just maybe, the Admiralty should slow down and reconsider. Parsons watched his momentum collapse and did the only thing he knew how. He invited the skeptics back to Newcastle. Again, he ran more tests, published more data, proved that Viper and Cobra's turbines had performed flawlessly even as their hulls failed. The engines weren't the problem. The ship design was... Slowly, painfully, the Navy started listening again. Turbines were fitted to experimental cruisers, then to larger destroyers with reinforced hulls. The ships worked. No catastrophic failures, no mysterious breakdowns, just speed, reliability, and fuel efficiency that piston engines couldn't match. By 1905, the Admiralty made the decision official. Every future Royal Navy vessel would be turbine-powered. No exceptions. The age of reciprocating engines was over. And then, in December 1906, HMS Dreadnought entered service and changed naval warfare forever. She was a floating fortress, but what made her revolutionary wasn't her guns. It was her propulsion. 4 shafts, 10 turbines, 23,000 horsepower. Parsons turbines, scaled up to sizes nobody thought possible, driving the most advanced battleship on Earth. Dreadnought could hit 21 knots, faster than any battleship afloat, and maintain that speed across oceans. She could outrun anything she couldn't outfight. The impact was seismic. Every battleship built before Dreadnought became obsolete overnight. Germany saw it and panicked. America accelerated its own Dreadnought program. Japan followed. Within 5 years, every major naval power on Earth was building turbine-powered battleships, and every single one of them was licensing designs based on Parsons' work. The man they'd dismissed had just redefined global naval architecture. But whilst the Navy was building dreadnoughts, Parsons was already thinking bigger. Warships were one thing. The real prize was civilian shipping, the transatlantic liners that moved people and prestige across oceans. And the competition for speed on those routes was about to get vicious. The British government had a problem. Germany was building faster passenger liners and threatening to dominate the lucrative transatlantic route. National pride was at stake, but so were millions in revenue. Mail contracts, passenger fares, and international prestige all flowed to whoever could cross the Atlantic fastest. In 1904, the government approached Cunard with an offer. Build 2 ships capable of averaging 24.5 knots across the Atlantic. Make them faster than anything Germany could field, and we'll subsidize the construction. One condition: they had to be convertible to naval auxiliaries in wartime. Cunard assembled a commission of the best naval architects and shipbuilders in Britain to decide on propulsion. The question was simple: turbines or piston engines? The commission reviewed Parsons' data, studied the dreadnought's performance, and made a decision that shocked conservative shipbuilders. Turbines, exclusively. No backup pistons, no hybrid systems, pure turbine power or nothing. In 1907, RMS Mauretania and RMS Lusitania launched within months of each other, and they were floating palaces powered by Parsons machines. Mauretania was the larger of the two, 790 feet long, displacing over 30,000 tons, fitted with turbines producing over 70,000 horsepower. That was more power than most battleships carried: 4 shafts, 25 boilers, steam pressure so high it required entirely new safety systems. On paper, she should have been a mechanical nightmare. Instead, she was a miracle. Mauretania's maiden voyage shattered every expectation. She crossed the Atlantic at an average speed of 26 knots, faster than any liner in history, and passengers barely felt the engines running. No vibration, no rattling silverware in the dining room. People danced in the ballrooms whilst the ship tore through the ocean at speeds that would have shaken a piston-driven vessel to pieces. One passenger wrote that traveling on Mauretania was like riding inside a cloud that happened to be moving faster than a train. The Blue Riband, the unofficial prize for the fastest transatlantic crossing, went to Mauretania in November 1907, and she kept it. For 22 years, no ship on Earth could beat her record. German liners tried and failed. American ships came close, but never quite matched her sustained speed. 2 decades of absolute dominance, and it all came down to Parsons' turbines running so smoothly that passengers forgot they were on a ship doing 26 knots through open ocean. Lusitania performed almost identically, and together the two sisters became symbols of British engineering supremacy. They weren't just ships, they were statements. Europe's elite paid premium fares to cross on them. Newspapers covered their voyages like sporting events. When Mauretania docked in New York, Crowds gathered to see the fastest ship in the world. The turbine had conquered war, and now it was conquering commerce, prestige, and public imagination. Cunard's profits soared. Other shipping lines scrambled to retrofit their fleets with turbines. White Star Line ordered turbine-powered ships, including one particularly famous vessel that would launch a few years later: Titanic. By 1910, nearly every major passenger liner under construction was turbine-powered, and Parsons' company in Newcastle was licensing designs to shipyards across Europe and America. The machines that admirals had called impractical were now driving the most luxurious vessels humanity had ever built. But Parsons wasn't finished. Whilst Mauritania was setting records, he was already pushing turbine efficiency higher, experimenting with geared systems that could extract even more power from steam. His workshop never stopped iterating, measuring, refining. The same obsessive precision that had built Turbinia was now improving machines that powered everything from battleships to ocean liners to the electrical grids lighting Britain's cities. Recognition finally caught up with the work. In 1911, Parsons was knighted for services to engineering. The shy Irishman who'd spent his career avoiding public attention now had a title to match his father's earldom. He hated the ceremonies, but accepted the honor because it meant the establishment had finally, grudgingly, admitted he'd been right all along. By the time the First World War erupted in 1914, Parsons' invention had become the backbone of British power. Every major warship that steamed out of Portsmouth, Scapa Flow, or Gibraltar was turbine-driven. The Grand Fleet that blockaded Germany, the destroyers that hunted U-boats, the cruisers that protected convoys across the Atlantic, all of them ran on technology that had started in a Newcastle workshop 20 years earlier. The Royal Navy's ability to project force faster and farther than any rival came down to one man's refusal to accept that piston engines were good enough. But the war took a piece of Parsons he never got back. His son, Algernon George Parsons, served as a major in the Royal Field Artillery. In 1918, with victory just months away, he was killed in action, 31 years old. The boy who'd grown up surrounded by turbines and engineering drawings, gone. Parsons buried him quietly and went back to work because the only thing he knew how to do with grief was measure it, contain it, and keep moving forward. His wife Catherine and daughter Rachel channeled their own loss differently. In 1919, they co-founded the Women's Engineering Society, fighting to open a profession that had been closed to women since the Industrial Revolution began. Rachel had studied engineering at Cambridge, one of the first women ever admitted to the program, and spent the war years working in her father's factories, whilst men were away fighting. When those men returned and pushed women back out, she refused to go quietly. The same stubbornness that made her father rebuild turbines 7 times until they worked now drove her to dismantle institutional barriers 1 brick at a time. The society still exists today, still fighting battles Parsons would have recognized. Parsons himself kept pushing boundaries. By the 1920s, his turbines were generating electricity in power stations across Britain, Europe, and America. Cities that had been lit by gas lamps a generation earlier now glowed under electric light produced by machines he'd designed. Factory floors ran on turbine-generated power. Entire industries depended on the continuous, efficient energy his invention provided. The principle was spreading beyond steam. Engineers were experimenting with gas turbines, jet engines, technologies that would eventually power aircraft and reshape the 20th century. All of it traced back to Parsons' fundamental insight. Continuous rotation beats reciprocating motion every single time. In 1927, he became the first engineer ever admitted to the Order of Merit, one of Britain's highest honors, limited to just 24 living recipients and personally awarded by the King. The shy man who'd avoided public attention his entire life now stood alongside the nation's greatest scientists, artists, and military leaders. He accepted the medal and went back to Newcastle, back to the workshop floor, back to measuring things other people assumed. On the 11th of February, 1931, Sir Charles Parsons passed away aboard the steamship Duchess of Richmond, whilst on a cruise to the West Indies with his wife. He was 76. The official cause was neuritis, but colleagues suspected exhaustion finally caught up with a man who'd never learned to stop working. His funeral was modest, attended by engineers, factory workers, and sailors who understood exactly what he'd given them. The newspapers called him the father of modern power. Historians would later rank him alongside James Watt and Michael Faraday as one of the architects of the industrial age. Turbinia, the little boat that had humiliated the Royal Navy and changed history, survived him. She was nearly destroyed in 1907 when a ship being launched across the Tyne lost control and almost cut her in half. Parsons had her repaired. In 1926, with no further use for the vessel, the company offered her to the Science Museum in London. They didn't have room for the whole ship, so they cut her in two. The aft section, complete with engines and propellers, went to London. The forward half stayed in Newcastle. It took until 1959 for someone to realize what they'd done and put her back together. Today, she sits in the Discovery Museum in Newcastle, fully restored, a reminder of what one engineer with a temper and a refusal to quit can achieve. The turbine never stopped evolving. Modern gas turbines power jet aircraft. Steam turbines still generate most of the world's electricity. Nuclear reactors use turbine systems descended directly from Parsons' designs. Every time you turn on a light, there's a decent chance the power came from a machine that works on principles he perfected over a century ago. The world runs on continuous energy, smooth and efficient, exactly the way he imagined it should. Parsons once said, "The object of all invention should be the elimination of waste. Waste of energy, waste of time, waste of human potential." He spent his life chasing that goal with obsessive precision, and he succeeded beyond anything the establishment thought possible. The man they ignored became the man they couldn't function without, and the boat they tried to chase at Spithead is still sitting in Newcastle, waiting for the next generation of engineers to see what happens when you refuse to accept that something can't be done.